Section 4.6, orthogonal vectors in Rn. Orthogonal is a general term which we use in higher dimension for perpendicularity. Remember in R3 when you took the dot product of two vectors, that was the definition of the dot product, where A was x1, x2, x3, B was y1, y2, y3. So the dot product gave us the summation of the what? Product of the corresponding components of each vector, and at the end of the day we end up with a scalar. So this guy is a number. Also, the dot product was also alternatively defined as magnitude of A plus times magnitude of B times cosine of the angle between what? The vectors, and theta goes between 0 and pi. The magnitude of A was square root of x1 squared, x2 squared, x3 squared, and the summation of those. Similarly for B. Also remember, if the dot product of two vectors was 0, that meant what? The vectors were perpendicular to each other. In higher dimension like Rn, we used the terminology what? Orthogonality. And for the magnitude of the vector, we use the word norm, N-O-R-M. So the definition is this. So that was in R3. Now, if you extend this idea of dot product to Rn, so now our typical vector will have n tuples of real numbers, and let's say y is n other tuples of real numbers. So between the standard inner product, that's what we call dot product in higher dimension, inner product in Rn, as here's the notation, x1 y1 plus x2 y2 all the way to what? X and yn. And the norm of the vector in higher dimensions is square root of x1 squared plus x2 squared all the way to xn squared. For example, imagine you have two vectors in R5, so that would be fifth dimension. So in order to find the inner product of these two vectors, you follow this formula right here. And then the answer comes up to, as you have noticed, I have multiplied 1 by 2, negative 1 by 1, 0 by 1, 2 by 3, and 4 by 0. And at the end of the day, I came up with 7. I can also find the norm of the vector in any dimension. And here's the norm of x, which is square root of 22. And here's norm of y, which is square root of 15, which I use this formula right here. Notice we don't call the length because it doesn't make sense. You're in higher dimension. So we call it the norm. Basic properties of a standard so-called inner product in Rn. If all x and y and z happens to be in Rn and k is a constant, the inner product of a vector by itself is always greater than or equal to 0. The only time it's going to be 0 if the vector itself is equal to 0. This is called positivity axiom. The inner product of y and x is x and y, so that means we have a symmetry. So the order doesn't matter. However, if the first component, not the second component, the first component has a scalar multiple, you can pull that out. If the second component had the scalar multiple, you have to switch these guys and make sure what? Due to the symmetry, you can switch it. And then what? Pull the scalar from the first component, not the second component. So be careful. This is a bit tricky property. If the first one has sum of two vectors and you take in the inner product of x plus y with z, so the answer is inner product of x and z plus inner product of y and z. This property does not apply to Rn. It applies to what? Any real vector space or even complex vector space. In other words, instead of saying let x and y and z be a what? A vector in Rn, you can say let U and V and W be in any arbitrary vector space, and let's say K is a real number. And if these four conditions are satisfied, then we say the real vector space together with inner product defined here uh, forms a real inner product space. So for a vector space to form an inner product space, you have to satisfy these four conditions: positivity, symmetric, and this is called homogeneity, and this is um, the fourth property, which is like if you take the inner product of the sum of two vectors with the third vector, then you would have what? The inner product of the u and w plus the inner product of v and w. Okay. For example, suppose the vector space is a continuous, all set of all continuous functions on a closed interval. We define the inner product of two functions in that space as the definite integral of fx times gx dx, where x goes from a to b. And k is a real number, correct? And h and f and g happens to be what? A continuous function in a closed interval. Then we can prove that one does define an inner product space in the vector space, what? Set of all continuous functions. So all we have to do is what? Go over the properties of what it takes for a space to be inner product space. First one is positivity. So take the inner product of f with f, but notice how the inner product is defined. So if you go replace this g with f, you get definite integral of f of x squared from a to b, which is a positive number because the function is positive. So the area underneath the curve, which lies entirely above the x-axis, is also positive. If we take the inner product of g with f, this is how the inner product is defined. That was given in the problem. But due to the properties of the integrals, because these are real value functions, I can switch these guys around, right? And then that would be exactly the same as the inner product of f with g. So the inner product of gf, I just proved that it's the same as product of f and g, which that kind of proves the symmetry. This guy, homogeneity axiom. So kf inner product with g, the inner product of kf with g, that's kf of x times g, according to the way the inner product is defined in this particular problem. So due to the properties of antiderivatives, I can pull the k out because k is constant. But now this integral is exactly the definition of inner product of f and g. And the last one, the inner product of f plus g with a third function h, that would be the same as f plus g of x times h of x, the antiderivative, x goes from a to b, due to the properties of the real value functions and definite integrals of single variables. You can split this and then separate the summation of the integrals, then again due to the properties of the integrals, and lo and behold, this guy is by definition the inner product of f and g, f and h, plus the inner product of g and h. So equation number one right over here does define an inner product in in the vector space of continuous functions. So it does define the inner product space because all four conditions were satisfied. So now the consequence of this inner product space are two important conclusions. One is Cauchy-Schwartz inequality, which says the absolute value of the inner product of the u and v, any random vector in a vector space, in an inner product space, is less than or equal to product of their magnitudes. So this is super important relationship when you're proving um, problems in this section. The consequence of Cauchy-Schwartz inequality is you can find the angle between two vectors in any inner product space, just like before theta goes from 0 to pi. What I'm saying is you can find the angle between two functions. You can find the angle between two matrices. So this is that general form. It's that general. It's very general formula. It's not just for vectors. It could be for functions, matrices, and so on and so forth. We also have something called triangular inequality, which means the magnitude of what? U plus V in inner product space is less than or equal to what? Magnitude of U plus magnitude of V. For instance, let's take a look at this example. Remember, you have two vectors in R4, you're in a 4 dimension. How would you find the angle between these two vectors in 4 dimension? Notice the formula is pretty much the same, except instead of dot product, we have inner product. So what you do, you find the inner product of u and v, which is -5, inner norm of u, which is square root of 15, and norm of v, square root of 13, and plug it into this formula. And lo and behold, you get this negative number. Take what? Cosine inverse of this guy, and you get 1.937 radians, or 190 degrees and 58 seconds. Keep in mind, theta has to be between 0 and what? Pi. Then we have something called orthogonal set of vectors. Orthogonal, remember, is the general term for perpendicularity. An inner product can be used to define the angle between two non-zero vectors, and if what? The inner product of two vectors in inner product space is 0, that means theta has to be what? Pi over 2. If you remember, this is how theta was defined. Remember, cosine of theta was inner product of u and v divided by norm of u times norm of v, where theta goes between 0 and pi. So, definition, let V be an inner product space, so that means all 4 properties have been satisfied. When you say let V be an inner product space, so that implies these 4 conditions have to satisfy, correct? Positivity, symmetry, homogeneity, and the last one. All right. Let U and V be in V or orthogonal vectors if and only if their inner product is 0. However, in general, the set of vectors v1 through vk is called orthogonal set of vectors if the inner product of vi with vj is equal to 0, where the subscripts are not the same. In other words, this implies in words that every vector is orthogonal to every other vector, not itself. That's why the subscript should not match. A vector v in the vector space V is called a unit vector if the norm is 1. An orthogonal set of vectors, okay, orthogonal set of vectors is called orthonormal set of vectors if what? If the inner product of every vector with any other vector is 0, and what? The norm of what? The vectors happens to be equal to 1. In other words, the inner product of the vector by itself should be 1. Okay, so basically that's the definition of orthonormal set of vectors. They are orthogonal, but they happen to have a what? Norm equal to 1. All right, so suppose we're trying to verify that these vectors are what? These are orthogonal set of vectors. So what does that mean? That means if I take the inner product of each of these with the remaining 2, I should get 0. How would I show that these orthogonal set of vectors are orthonormal? So First of all, check and see that the inner product is equal to 0. So you can what? Check the orthogonality condition. And then what you do, once you made sure they're orthogonal, that means they're perpendicular to each other, right? Not to themselves, but to each other. Then you divide both, each of them by their corresponding norms. And the result is called a set of orthonormal vectors. What is the relationship between orthogonality and the solution of homogeneous system of equations? If you rewrite, suppose this is the matrix of coefficients, okay, and this is like a matrix of variables. So in order to get 0, we're supposed to take the dot product of each row by what? This column vector, which means I have to take v1 dot x, v2 dot x, excuse me, vm dot x equals 0. So x is the solution of what? We can just claim x is the solution of this homogeneous system of linear equations if and only if x is orthogonal to each vector in the row space of matrix A. So you take every row and dot it with what? This column vector. You get 0 because, you know, it's a homogeneous system. So therefore the solution, instead of saying the solution, now we're going to use a different verbiage, which is like what? We're going to call x, you know, it used to be called solution. We're going to call it orthogonal. What? X is orthogonal to each vector in the row space of matrix A. Question is, what's the purpose, or I should say some application of orthogonality, or ultimately orthonormal set of vectors? Well, turns out that what? They are used what? You know, you can find the basis for what? An orthonormal basis for subspace of what? Rn, of Rn. Computationally, they are easy to work with. And they're also used in signal analysis and functional analysis, which they are like higher. This functional analysis is like then higher level math course, which the requirement is linear algebra, and signal analysis is like what? Engineering course. So the next item is called orthogonal complement, which is, this is the notation. Let's say we have the notation. So you have a subspace like W, and then there is a superscript like perpendicular lines. So remember, U and V are in Rn are orthogonal to each other, not to it themselves, if their dot product is 0. That would be like in like R3. In Rn, we use the what? Inner product. We don't use that notation. We use this notation. If this inner product is 0, then we say the vectors are orthogonal. However, if what? Set of all, notice the catch is now all, not just one, all vectors z that are orthogonal to W, all right, and W is a subspace of Rn. So maybe I should define this first. The fact is, if vector z is orthogonal to every vector in a subspace W of Rn, so W is a subspace of Rn, then z is said to be orthogonal to the subspace W. However, the set of all vectors z that are orthogonal to W, all vectors, not just single vector, every vector z that are orthogonal to W is called orthogonal complement of W, and it's denoted by this notation. And you read this as W perpendicular, or simply people read this as W perp. W perp, which is, you know, is just a short way of saying perpendicular. So what is the definition? The definition of W perp is all values of z in vector space V such that what? The inner product of z and w is equal to 0 for every vector w in the subspace w. This is a little w, this is a capital W with no arrow, where the capital W with no arrow is some subspace of your Rn. In other words, let W be a plane. So here's an example. Let W be a plane through the origin in R3, and let L be the line through what? The origin and perpendicular to the plane. Okay. If Z and W are non-zero vectors, where Z is on what? On line L, and W is on the plane, correct? W is the vector W is in that W plane, which goes through the origin as well. So, the line segment from 0 to what? To Z, right here, is perpendicular, what? The line segment from Z to 0 to W. So this line segment is perpendicular to that line segment. That is what? Their dot product is what? 0. So each vector in L, so each vector you select in L is orthogonal to every vector in what? In W, correct? In fact, L consists of what? All vectors that are orthogonal to W's in W space, and W consists of all vectors orthogonal to Z's in L. That is, L is orthogonal what? Complement of W, and W is orthogonal complement of L. So that would be an example of what orthogonal complement of a subspace is, or how it should look like. It's an example. That's not the only example, of course. Then we have facts about the what? Orthogonal complement of a subspace with W as subspace of a bigger space called, let's say we call this B. The vector x in what? Orthogonal complement is in orthogonal complement if and only if x is orthogonal to every vector in a set that spans W. Notice the catchwords are every vector, not just a single vector. Orthogonal complement of W is always a subspace of a what? Of a vector space, like in this case, Rn. This diagram shows a plane and a line through what? 0 origin as orthogonal complement. So let's finish this section with a quick example. Suppose you got two vectors in R4, correct? And suppose these guys span a subspace W of R4. In other words, they span the W. And W is a subspace of a vector space R4. You know what the span is. That means any vector you select in W, you can write it as linear combination of these two guys. Question is, can you find the basis for the orthogonal complement of W? Orthogonal complement of W. Sure. Remember what orthogonal complement is. A set of vectors such that what? You take the dot product of those vectors which you select in the orthogonal complement, which happens to be the subspace of Rn. You take their dot product, you should get 0. In other words, the set of all vectors dotted with this guy should be 0. Dotted with the second guy should be 0. So what you do is, because these guys are equal to 0, so what happens is, if you write it in the standard form and call these guys like the coefficients of x1, x2, x4, augment this with 0, 0. So you're going to end up with, let's say, what? A homogeneous system of equation. Well, turns out the what? The way we get a basis for the orthogonal complement is this. Form this homogeneous system of linear equation. Hence the solution space, not the solution, but the solution space of what? This homogeneous system of equation is, in this particular case, is what? Described parametrically by these equations. Notice when you put the augmented matrix in what? In row echelon form or reduced row echelon form, you're going to get this. Keep in mind that the what? First and the second column has leading 1, but the third and the fourth, they don't. So what happens is we're going to let x3 to be t and x4 to be r, where t and r are what? Real numbers, correct? Real numbers. So those are free variables. So x2 and x1 has to be expressed in terms of what? T and r. So the solution, you have infinite many solutions, and this is how the solutions to this homogeneous system of linear equation looks like. However, if you kind of rewrite this in terms of linear combination of these two vectors, simply factor out the t plus factor out the r, you get this. So turns out, remember r and t is any real number. So turns out that what? The orthogonal complement of W is two-dimensional subspace of R4. Two-dimensional because I only have two linearly independent vectors which they span the what? The orthogonal complement of W, the W space, which is the subspace of what? R4. So the orthogonal complement of W is the two-dimensional subspace of R4 with the basis the following, these two vectors. The conclusion here, these guys form a basis for what? For orthogonal complement, which happens to be what? Which W happens to be what? The subspace of R4. So the basis for what? Orthogonal complement of W has these two vectors in it. Therefore, the dimension of the what? Orthogonal complement of W is 2. Thank you.